Welcome back to ByteLearn. So far, we have covered client-server architecture, databases, and distributed systems. Now we need to talk about performance. Not vaguely, not just make it fast, but precisely, because in system design, fast means two completely different things depending on what you're building. Amazon ran an internal study and found that every 100 milliseconds of added latency, 1/10 of a second, cost them 1% in revenue. At Amazon's scale, that is approximately $1.7 billion per year for a delay you cannot even consciously perceive. This is why latency is not just a performance metric, it is a business metric. But latency alone does not tell the whole story. YouTube receives 500 hours of video every single minute. No amount of low latency optimization will help you process that. You need throughput, the capacity to handle enormous volume, and these two metrics pull in opposite directions. That is what this video is about. In this video, we define latency and throughput precisely. We will show you exactly where each one breaks down in a real system. We will trace a request end to end and label every millisecond. And at the end, we will give you a two-question decision framework for any system design problem. In an interview, this video is for engineers who have built systems and wondered why performance degrades under load, and for candidates preparing for system design interviews where the optimization question almost always comes down to latency versus throughput. We will flag the interview critical moments as they come. Stay till the end. We will show you how one well-designed system solves both metrics simultaneously, not by choosing one over the other, but by routing each type of work to the right architectural layer. Most candidates in interviews pick one and ignore the other. You will not. One prerequisite: watch the distributed systems video in this series. First, we build directly on horizontal scaling and load balancers. If you have already watched it, you are ready, let us go. There are exactly two ways a well-written system fails in production under load. The first, latency failure. Users experience slow responses. The page takes 2 seconds. Engineers add more servers. Nothing changes because more servers cannot fix a slow database query. The second, throughput failure. The system works perfectly in testing, handles 100 users fine, and then collapses when traffic spikes. Queues fill up. Timeouts cascade, the CPU red lines. These are two completely different failure modes and they require completely different solutions. The cost of throughput failure is equally dramatic and equally well documented. Every IRCTC Tatkal window, 10 a.m. for AC classes, lakhs of people hit the site simultaneously. The system has crashed, timed out, and served error pages repeatedly over the years. The booking itself, when it works, takes a few seconds. The problem is not latency, it is throughput. The system cannot handle the simultaneous load, and adding a CDN does not fix this. You need more application server capacity, better queue management, and a database that can handle concurrent write contention. Latency failure and throughput failure are different diagnoses requiring different treatments. Here is the most common and expensive mistake in production engineering and the most disqualifying answer in a system design interview. A request is slow. An engineer adds more servers. Latency does not improve. Why? Because if a database query takes 300 milliseconds, distributing load across 10 servers still means every individual request pays that 300 millisecond cost. Throughput went up. Latency stayed the same. The fix for slow latency is a cache, a CDN, or a faster query, not more instances. The fix for low throughput is more workers, queues, and horizontal scale. Knowing which tool to reach for which problem is what separates senior engineers from junior ones. Think of it as two separate levers in your system. The latency lever moves data or computation closer to the user. CDNs, Redis caches, pre-computed results. The throughput lever adds processing capacity, more servers, message queues, async pipelines. The most important insight in a mature system: you pull both levers independently for different paths. The user-facing read path gets the latency lever. The background write and processing path gets the throughput lever. You do not choose between them. You apply each where it belongs. Latency is the time it takes for a single request to travel from the user to the system and back. One user clicks a button. How long until they see the result? That gap measured in milliseconds is latency. It is the metric users feel directly. No user has ever thought this system has great throughput, but they have definitely abandoned a page because it felt slow. Latency is not one thing, it is the sum of three delays. Network round trip time, the time packets spend traveling across wires and routers. Processing time, the time your server actually spends computing a response. And queuing delay, the time your request spends waiting in line because the system is busy with other requests. All three add up to what the user experiences as slowness. Throughput is the total volume of work a system can complete per unit of time, measured in requests per second or megabytes per second. One user sees latency. The entire system produces throughput. A single ATM transaction might complete in 300 milliseconds. That is its latency. Whether the banking system can handle 10,000 simultaneous withdrawals, that is throughput. Throughput is limited by physical resources. CPU cores, only so many threads can execute simultaneously. Memory bandwidth, only so much data can move between RAM and processor per second. Disk and network I/O both have hard limits, and concurrency design, a poorly written single-threaded server, wastes all of those resources. Throughput is the ceiling imposed by hardware and architecture together. The clearest analogy, the Mumbai-Pune Expressway. Your latency is how long it takes you personally to drive from Pune to Mumbai. The expressway's throughput is how many cars can make that journey per hour. A two-lane expressway might let you drive at 120 kilometers per hour low latency, but it can only fit 3000 cars per hour limited throughput. A 16-lane highway has higher throughput but does not make your personal drive faster. Two different problems, two different solutions. Let us trace a single user request and see exactly where latency accumulates. Three parties, your browser, the application server, and the database. We will put a millisecond counter on every hop. The browser sends an HTTP request. The packet travels across the internet, through routers, past ISP peering points, across undersea fiber, even at near light speed, reaching a data center in a different city, costs 15 to 50 milliseconds. This is network round trip time. You cannot eliminate it. You can only reduce it by bringing data geographically closer, which is what CDNs do. The app server receives the request and queries the database. If the data is not in memory, the database performs a disk read. Disk I/O adds 10 to 50 milliseconds. A single page at Swiggy might involve 5 database queries, each one adding to the total. This is why databases are almost always the primary latency bottleneck in web systems. The database returns the result back to the app server. This hop is within the same data center, a private, low latency network under 5 milliseconds. The app server processes the data, formats a response. The app server sends the HTTP response back across the internet. Another 15 milliseconds total round trip for this clean unloaded request, around 52 milliseconds. That feels instantaneous. The user is happy. Now put this server under load, 500 concurrent requests. The app server has 8 CPU cores. 492 requests are sitting in a queue waiting for a free thread. Your request arrives and waits 450 milliseconds before even being picked up. The actual processing takes 52 milliseconds, but the user waited 502 milliseconds. This is queuing delay, and it is why a system that feels fast in testing becomes unusable at production traffic. Visualize throughput. 1,000 requests per second are arriving. With a single application server, you hit a ceiling almost immediately. The server's 8 CPU cores are fully saturated. New request queue, latency spikes, users experience slowness. Your throughput is capped by the single machine. This is not a software problem, it is a physical resource limit. Add two more servers behind the load balancer. The load balancer distributes the 1000 requests per second evenly. 333 per server. Each server runs at about one-third of its CPU capacity. No queuing. Latency drops back to the 52 millisecond baseline. Throughput triples. This is horizontal scaling solving a throughput problem. Notice what did not change. Each individual request still takes 52 milliseconds. The latency from browser to server and back is the same. Adding more servers increased the system's capacity. Its throughput. It did not make any single request faster. These are two separate problems. Latency is determined by the critical path. Throughput is determined by available parallelism. To actually reduce latency, you need a different tool. Put a cache in front of the database. A Redis cache returns a result in under a millisecond, eliminating the 20 millisecond disk read. Latency drops from 52 to 32 milliseconds. The cache solved a latency problem. The extra servers solved a throughput problem. Same system, different solutions for different metrics. The design goals are fundamentally different. A latency first system is optimized to make each user interaction as fast as possible, often at the cost of efficiency. A throughput first system is optimized to process the largest possible volume, even if each individual item takes longer. Their architectural toolkits diverge sharply. Latency first systems use CDNs to push data geographically close to users, Redis caches to eliminate slow database queries, and pre-computation to have answers ready before the question is asked. Throughput first systems use Kafka or SQS to buffer work batch processors to amortize overhead, and parallel worker pools to run thousands of tasks simultaneously. They fail differently. Latency first systems are fragile against slow dependencies. One slow database query turns a 50 millisecond response into a 2-second response. Everything else is fine. But this one bottleneck is catastrophic. Throughput first systems degrade gracefully. As load increases, processing slows proportionally, but nothing catastrophically fails. They handle overload with back pressure. Stock trading systems require sub-millisecond latency. A 10 millisecond delay can mean executing an order at the wrong price. Payment authorization must be instant for user trust. On the other side, ML training, video encoding, and ETL pipelines do not care if a single item takes 30 seconds, as long as the system processes millions of items per hour. No one is watching a loading spinner on a batch job. Many systems need both, but they solve each concern in different layers. Netflix video playback is latency critical, served from CDN edge nodes for sub-second startup. Video transcoding is throughput critical, runs as a massive batch pipeline across thousands of machines. The insight is to separate the user-facing path from the background path. Route each to the right architecture. You do not have to choose globally. Let us trace a complete system and see where both metrics appear. A user clicks a button, the latency clock starts immediately. Every millisecond from this point is latency the user will feel. The first hop hits a CDN edge node close to the user. Static assets, images, JavaScript, CSS are served in under 5 milliseconds. Latency optimization 1. Bring data geographically close to users. No database involved. The API request reaches the load balancer. Its job is to maximize throughput. Distribute requests evenly across a fleet of application servers so no single machine becomes the bottleneck. Throughput optimization 1. Horizontal distribution. The load balancer picks a healthy app server and forwards the request. This is where business logic runs, validating the user, assembling the response, deciding what data to fetch. Before hitting the database, the app server checks Redis cache, hit result returned in under a millisecond. The 20 millisecond database query is completely eliminated. Latency optimization 2. Cache what you read frequently. For writes, the system queues the database update asynchronously. The user receives an instant confirmation response. The database commit happens in the background. This is the same pattern Swiggy uses for order placement. The user sees order placed instantly. The kitchen notification arrives a moment later. Latency to user is decoupled from throughput to database. The app server sends the response back through the load balancer to the user's browser. The latency clock stops the full journey CDN edge, load balancer, app server, Redis cache, async DB write completed in around 20 milliseconds from the user's perspective. End result, users see responses in around 20 milliseconds. The system handles 50,000 requests per second. Two problems solved independently in the same architecture. The user-facing path is latency optimized with CDN and cache. The backend write path is throughput optimized with async queues. This is how production systems at Swiggy, Razorpay, and Hotstar actually work. In a system design interview, the optimization question always comes. You have just designed a food delivery app, a payment gateway, a data warehouse. The interviewer asks, how would you make this faster? Here is a two-question framework that will always lead you to the right answer. First question, is a human watching a loading spinner right now? If yes, latency is the primary metric. Research shows users tolerate 200 milliseconds for an instant response. Beyond 1 second, engagement drops sharply. If a system or a batch job is waiting, no human is tapping their fingers. Optimize for throughput. Volume is what matters. Second question, find the constraint before you optimize. If the bottleneck is network distance, use a CDN. If it is compute saturation, add horizontal servers. If it is database I/O, add a cache for reads or an async queue for writes. Never optimize blindly. The only correct answer is measure first, then fix the specific constraint. Every other answer is a guess. The answer that will distinguish you in any senior system design interview is this. You do not have to choose one metric globally. Separate concerns by path, the user-facing read path, latency critical, serve from cache and CDN. The background write and processing path, throughput critical, use message queues and batch workers. When you say this, you have shown you understand how production systems are actually built. The answer that will hurt you, we can just add more servers without identifying where the time is going. More servers increase throughput. They do not reduce the latency of a slow database query. If the user is waiting on a 300 millisecond database call, adding 10 more servers will not help a single user. Adding a Redis cache will cut that to 1 millisecond. Know the bottleneck, fix the right thing. Stop for a moment and think about what life looked like in India before these engineering problems were solved at scale. A bank transfer took 2 to 3 days to clear because batch processing systems could not handle real-time throughput. Booking a train ticket meant physically standing at the station counter because the alternative, a web app serving a billion users simultaneously, had not been built yet. Watching a live match meant a cable subscription because streaming 50 million concurrent viewers required a throughput architecture that did not exist for most of the 2000s. These are not just software problems, they are latency and throughput problems, and solving them change everyday life. The UPI revolution is at its core a latency engineering achievement. When you tap pay on PhonePe, the system validates your PIN, checks your bank balance, debits your account, credits the recipient, and sends you a confirmation, all in under 1 second. That sub-second response is a latency guarantee baked into the NPCI architecture. Before UPI and EFT batch transactions, your transfers sat in a queue and cleared 4 times a day. Solving the latency problem, getting every payment confirmed in real time is what made 8 billion transactions a month possible. And it is what allowed a vegetable vendor in Vijayawada and a migrant worker in Surat to participate in the digital economy. Hotstar's IPL streaming challenge is one of the most cited throughput engineering achievements in the world. During major IPL finals, they have served over 50 million concurrent video streams. Think about what that means. Architecturally, each viewer needs a smooth, low latency stream. That is a per user latency problem. But serving 50 million of them simultaneously is a throughput problem of an entirely different order. You need CDN edge nodes distributed across India, origin servers with enough combined bandwidth to feed every edge simultaneously, and ingestion pipelines that can encode incoming broadcast feeds at the speed they arrive. Hotstar's 2023 World Cup streams were a throughput benchmark the entire industry studied. It could only happen when both metrics were solved: latency for each viewer, throughput for all of them together. On the National Stock Exchange, latency is not a performance metric, it is the product. NSE's co-location services allow trading firms to place their servers physically inside NSE's data center, connected by fiber, measured in centimeters rather than kilometers. The round trip from order submission to execution confirmation is under 500 microseconds, half a millisecond. Algorithmic trading firms spend tens of crores on hardware and colocation fees to shave microseconds off their order path. If your system is 1 millisecond slower than a competitor's, their arbitrage bot captures the trade before yours. There is no more extreme example of latency as a business critical constraint in India. And here is why this knowledge becomes even more valuable right now. Every AI system you use, ChatGPT, Gemini, Claude, runs on the same client server architecture with the same latency and throughput constraints solved in the same ways. Your prompt is an HTTP request. The response latency is the time from your submit to the first token appearing on screen. The GPU cluster's throughput is measured in tokens per second across all simultaneous users globally. OpenAI and Anthropic use load balancers, Redis caches for repeated prompt patterns, and message queues to manage inference backlogs. The same tools you now understand applied to a new generation of systems. The engineers who will build and scale AI products are the ones who understand these fundamentals deeply. That is you now. Here is the perspective worth carrying forward. Latency and throughput are not performance features you layer on top of a working system. They are architectural constraints that determine whether the system works at all under real conditions. Amazon's $1.7 billion latency cost, Hotstar's 50 million concurrent viewers, NSE's 500 microsecond order execution, UPI's sub-second confirmation. None of these are optimizations that were added later. They were designed for from the beginning in the architecture at the infrastructure level. Now you have the vocabulary, the mental model, and the framework to design for them yourself. That is latency versus throughput. Latency is the time for one request. The user feels every millisecond. Throughput is the volume the system handles. The business lives and dies by it at scale. They pull in opposite directions. The best systems solve them independently in different architecture layers. Now you know how. Here is exactly what you can now do. Explain both metrics precisely. Latency is the time for one request. Throughput is total volume per second, and confusing them costs you in interviews. Spot the real culprit: queuing delay, not raw processing time, is why systems fall apart under load. Apply the two-question framework in any system design interview, and architect a system that optimizes both metrics independently by separating paths, which is the real-world pattern behind every large-scale Indian tech product you use. Next video, caching. We have mentioned Redis caches multiple times in this series. Now we go deep. How does Redis actually work? Cache aside versus write through, when do you use each? What eviction policies should you choose? Link in the description. Subscribe to ByteLearn for one system design concept per week. Under 8 minutes, interview ready. Hit the bell. See you Wednesday. One question before you go. Which part clicked for you? The three components of latency, the Mumbai-Pune Expressway analogy, the queuing delay spike, or the layered architecture answer? Drop it in the comments. It helps me know which examples land, and it helps other engineers watching find the moment that made it clear for them.